if you don't, it's okay with me. I don't care.
So good evening, everyone. My name is Sean Mulcahy. I'm a faculty member here in the Department of Chemistry and Biochemistry. On behalf of my colleagues, it's my pleasure to welcome you to this evening's event. It's wonderful to see so many students, faculty, and staff from our campus here, but I also want to extend a special welcome to our guests from the wider community, those at other colleges and universities, as well as the Rhode Island section of the American Chemical Society. And of course, I'd like to welcome and recognize our honoree this evening, Professor Harry Gray, who is joined by his wife, Dr. Shirley Gray. Thank you both for being here. This evening's event is made possible by a grant awarded to the department from the Camille and Henry Dreyfus Foundation, which has been dedicated to the advancement of the field of chemistry for more than 70 years through various grant programs and awards aimed at improving human relations and circumstances around the world. One of those programs, the Jean Dreyfus Lectureship for Undergraduate Institutions, is the reason we are here tonight. Last year, Providence College was one of only 5 institutions nationwide to receive this award, which brings a leading researcher to campus to interact with students and faculty and to give a series of lectures. We are extremely delighted to have a true pioneer with us this evening. Professor Harry Gray is the Arnold O. Beckman Professor of Chemistry and founding director of the Beckman Institute at the California Institute of Technology. Born in Woodburn, Kentucky, Dr. Gray received his bachelor's degree in chemistry from Western Kentucky University. He then went on to receive his PhD in chemistry from Northwestern. After a postdoctoral fellowship at the University of Copenhagen, Dr. Gray earned his first faculty position at Columbia. In just 5 years, he rose through the ranks to full professor, and in 1966, he moved to CalTech, where he has been ever since. Dr. Gray is a giant in the field of chemistry. He has authored more than 900 research papers and 18 books over a career that spans more than 50 years. He's received numerous awards during his career, including the Welch Award, the Wolf Prize, and the American Chemical Society's highest honor, the Priestley Medal. He's an elected member of the National Academy of Science and the American Academy of Arts and Sciences. In 1986, he was recognized with the National Medal of Science from President Ronald Reagan. And in a testament to his teaching and mentoring abilities, he was also awarded the Richard Feynman Prize for Excellence in Teaching from CalTech. In short, his stature in the field is without question, and we are grateful that he has agreed to join us here on campus. After spending today interacting with our students and faculty, one senses immediately his humility, his thirst for understanding and knowledge, and an enduring desire to be a mentor to others that make him a perfect fit for advancing the mission of both Providence College and the Dreyfus Foundation. Here at PC, we value the pursuit of truth and the creation of new knowledge, and we encourage our students to use these skills to tackle serious problems facing society. And Dr. Gray will be speaking about some of those challenges today. His lecture tonight is entitled, Powering the Planet, Fuel from Sunlight and Water. Please join me in giving a warm welcome to Professor Harry Gray.
Great.
Thank you for coming.
That was great. Thank you. Well, thank you, Sean. That was pretty nice. I think I'm going to take you everywhere I go. If you can remember that intro, that was much more than I deserved. Well, I've had a wonderful day. I've met some of the really coolest students that I've met in a long time. You guys are just terrific. I don't know where you get all your enthusiasm, but everyone seems to be happy, enthusiastic here. I was so impressed with that poster session that you had with 2 different lines of science, and you knew everything about both lines, and going to pick one for your seminar. This is a terrific place. Dean, this is a terrific place. I want you to give raises to all the chemistry professors right away. Okay. Well, I'm off and running here. I'm stalling because I actually don't have a talk. Just kidding. Well, it's a real honor. I've known about the Dreyfus Foundation for a long time. I've interacted with them. Special shout out to my friend Nancy Gray and my brother Michael Gray. Now, we're not related, but we have the same name. Thank you guys for coming. My friends from Rhode Island College are here, and all sorts of good folks are here. It's a real pleasure to be here. So I'm going to talk about, did I get the school right? And I got the lecture right? Did I get the date right? I'm on a roll. I'm going to talk about the situation now in solar energy and the progress we've made to try to really build systems that will actually power our planet with sunlight, because we're going to need that, as you all know, and we're making great progress around the world on this. And I'm going to summarize this progress, at least in my program, and indicate some others tonight. My first slide shows you that we have plenty of sunlight. All we got to do is figure out how to convert it, because there's so much energy coming from sunlight that even if we can just convert just a small fraction of it, we can run our planet. And I'd like to say at this point that, not to make anybody in nuclear energy mad at me, but I like to say that I really like my nuclear power plant 93 million miles away. It's a very comfortable feeling. And so we're getting lots of photons, and so now over the last 10 years, scientists, and I have to admit a lot of applied physicists and engineers, have gotten the photovoltaic area to an incredible point where electrons, at least in California, are almost free. The price of electricity from sunlight in California has just dropped below the price based on natural gas. You can get electricity now from sunlight at 4 cents a kilowatt hour because of the enormous advances in physics and applied physics and the people who are making photovoltaic devices. We now have things that are well over 20% and very robust, sunlight to electricity, and we have ones coming along that are about 30%, and if you extrapolate now, it's my feeling we'll be at 40% sunlight to electricity before much longer. So the situation in the time that I've worked on this problem has changed dramatically, as I will indicate to you. But at the turn of the century, one of my students, and Nate Lewis is one of my students, I apologize for that. But Nate and I sat down and decided how much of the land area in the United States we'd have to cover to run the entire United States on solar photovoltaics. And there it is. We decided to cover an area of the United States where nobody lives, right in here. And nobody lives there. A few people live there, but we offered to move them to Beverly Hills. But this gives you an idea of how much land would have to be covered in 2000 to run the entire country on photovoltaics. This land area has not changed in these 18 years since we drew this map, because now instead of 3 terawatts, we need about 20 because of the enormous increase in usage of energy. And of course, what's counterbalanced that is the enormous increase in the efficiency of photovoltaics. And so this spot has remained the same because of much, much higher efficiency, mapping out with a much greater usage. But of course, Nate and I decided we wouldn't cover this. We might be unpopular if we did this. What's happening around the country, as you may know, is that people are covering wasted spaces with photovoltaics, especially parking garages. All the parking garages in California are being covered with photovoltaic roofs, which allows people to have local solar power stations, which we have at CalTech. We have 5 of those at CalTech now, Jack, and we send electricity to LA. We sell it during the day to LA, and we buy it back at night because, as you know, you have to store it. You get about 5 or 6 hours a day of photovoltaic electricity. So storage is the critical point, and storage is the subject of my lecture. We've got to store it, and one way to store it is by splitting water with sunlight. So I modestly admit that I started this off in terms of explaining to the world how to do this in 1981 in a paper with my student, Andy Maverick. With using metal complexes, we wrote a paper of how you can take light absorbers, which do 1 electron, 1 proton, and whole systems, and convert that with catalysts to make and break bonds so you can split water. I thought it was a pretty good paper, but I had then 2 very smart students named Nate Lewis and Dan Nocera. They're not only very smart, they're just slightly arrogant. And they think the old man needs some help. So they said, Harry, this paper is not that great. It's out of date. So they wrote this paper in PNAS in 2006, really straightening me out. But when my students do this to me, I immediately write another paper explaining in 1 page what they've actually said in a big technical paper that went on forever, Maria. It went on forever. You can explain it in a couple of paragraphs. So my advice to all of you is, if you want to read 1 paper in this field, please read mine. Right here. This is all to get the audience started in this talk, and the reason I put this slide up is there's another reason. There was a great event in the late 90s at NREL, the National Renewable Energy Laboratory, where John Turner's group built the first really working solar water splitter, the first artificial device that was over 10 times more efficient than natural photosynthesis. And if you stop to think about it, Michael, we've been living on natural photosynthesis, water splitting there, making all the sugars that have made all the oil, gas, and coal that we've been using for free and polluting the planet ever since. John Turner's group built a 12% water splitter that was robust and fantastic, and they showed us how to do it with a tandem semiconductor system, red light in, blue light in, and so forth. It was a wonderful design. There was only one problem, because if John Turner had solved the problem, this talk would now be over. And it's only 7:15, Sean, and you told me I had 45 minutes, so there must be something else. Here's the something else. This water splitter costs a fortune. It's full of platinum, chock full of platinum. Surely we need platinum for jewelry for you. We need platinum for best-selling albums. We have better uses for platinum than to split water and save the planet. And so at this point, when John Turner did this wonderful experiment to show us, hey, we can do this. When he published that paper, I had been in the field earlier, but had gotten out of it. I sat down and I said, you know what I'm going to do? I'm going to get a group together of really great chemists and physicists and theoreticians. I'm going to get a group together, and together we're going to build a water splitter just as good as John Turner's, but it's not going to have any platinum in it. It's going to have only elements that are scalable, things that are cheap, things that are earth abundant, things that we will never run out of, ever. That means it's got to be iron and nickel and cobalt, tungsten and molybdenum, manganese, things like that. And so I sat down and we decided to design systems that would work this way. We've got to have light absorbers and charge transport systems. We've got to capture all the sunlight that reaches the Earth's surface, filtered by the ozone layer. We've got to excite a system to an excited state, which then will do charge transport. We started with molecules that absorb the light and linkers that, with the donors and acceptors do fancy stuff. But we realized right away when we started this program that was never going to work, and we'd have to use semiconductors. We would have to use robust semiconductors that the physicists and applied physicists were developing here for this part of it. A semiconductor does both light absorption and charge transport. You excite a semiconductor, it separates electrons and holes, and the ball game you have to play is to get the electrons to make hydrogen and the holes to make oxygen before they recombine to make heat. If they recombine to make heat, you've just lost the ball game. But if you can keep them separated, the holes over here for oxygen, the electrons over here for hydrogen, if you can figure out how to interface catalyst right here with them to do that, you can in fact split water to hydrogen and oxygen. And this talk is about the light absorbers and the catalyst that we've made in our program. And of course, let me go back to the problem. Here are the three challenges, of course. It's obvious it has to be efficient. This whole system has to be at least 10% efficient or there's no point. Although natural photosynthesis for fuel is only 1% efficient, and we've been doing okay with that. But we have a long time. It's got to be at least 10% efficient, solar to fuel. It's got to be, obviously has to be robust. It can't break down, Maria. That's why we have a problem with molecules. But we've got to make them better. We've got to make them more robust. But molecules, even with thousands of turnovers, don't really survive long enough. So materials in this whole thing is where the sort of field is going, or we're still looking for good molecules. And your group has to do it. You've got to do it. Your group, I met your group today. You've got to do it. And I'm going to tell you exactly where you have to do it in a minute, okay? And of course, they've got to be scalable. No platinum, no iridium, no gold, no rhodium, not even ruthenium. It's got to be iron, nickel, cobalt. You got it? You got it? I know you're working on iron. Or nickel. Nickel too, I think. But iron, mostly iron. This is audience participation. It's just fine. Okay, so what do? I get together a bunch of people who actually are pretty smart. And here they are. I put together a program, first, Nancy, between CalTech and MIT. It was just me, Nate, Dan Nocera, Kit Cummins. We started the program. We said, if we can make a few catalysts that don't have platinum in them, that are almost as good as platinum, we got a pretty good start making hydrogen. And if we do that, we can go back to NSF and ask for big money. And we did. With 2 years, Dan and Nate and I and our students and postdocs made several really good hydrogen-evolving catalysts. And NSF then gave us this big program called CCI Solar, where we can put all these investigators around the world together in a program with the goal of making a solar water splitters that are very efficient but scalable and robust. A couple of theoreticians, Sharon Hammett Schiffer, who's moved around. When I started the program, she was at Penn State. She moved to Illinois. Before I could get this changed, she moved to Yale. And she moved so fast, but we're still sending the money to Illinois. I don't know who's using it. We have a theoretician named Julia Galley, who's at Chicago. And we've got people who make molecules. We've got Tom Jaramillo at Stanford. Dan Nocera moved to Harvard from MIT. We still have a chemical engineer, Paula Hammond, at MIT. You probably know Paula, Nancy. and catch. So this is our gang. We got people who make molecules, people who measure them. We got theoreticians. We got all kinds of people. We meet all the time. We communicate over the web. We're working together to solve this problem. And we designed a solar water splitter that could work with cheap materials. And it's based on the fact that we had already figured out how to synthesize these micro rods, silicon micro rods that are about 200 microns in the long direction. They're long and skinny. They're long and skinny because you've got to absorb all the sunlight that goes through them, so they're long. So you get all the light absorption. They're skinny because of what I told you. As soon as you excite them with light, and the top ones are blue light, the bottom one's red light, so they're tandem. They're long and skinny because what I told you is once you excite the semiconductor, the hole and the electron separate. They're skinny because we got to get the holes out to the surface fast and the electrons out to the silicon surface at the bottom fast before they recombine to make heat. So they're skinny, and that gives us an advantage in getting them out there fast enough, particularly if we can solve what's called the hole and electron tunneling problem, which I've done a lot of work on in my life. But we built these, the top ones are things like tungsten anode, tungsten oxide. The bottom ones are silicon. We figured out how to make these devices, and at MIT, Paula Hammond figured out how to make us a membrane, layer by layer membrane that transports both electrons and protons through a transparent membrane. It was a huge thing. So we've actually built this thing, although as I'm going to tell you, and it works, but I'm going to tell you we're not going to use it big time because we're going to use something else now, because what I told you, the physicists have now given us PV devices that are so efficient and so good. We're going to use those directly rather than this wireless thing with this membrane. But let's start the discussion here of the catalyst we've made that replaced platinum down here. Normally we'd put platinum on the silicon to make hydrogen, but we decided first, Maria, to put hydrogenase on it, your enzyme. Sadly, it doesn't work because although it's wonderfully efficient and one of the most efficient things ever, it's a protein. When you have protein on this silicon and light's coming in and all hell's breaking loose, this thing doesn't last very long. It's not robust enough. It's a protein. It's got a lot of wimpy organic stuff in it, and it's not hardcore inorganic. We're the Marines. The inorganic chemists are the Marines of chemistry. You got to remember that. And then, I put it on the silicon first, and we irradiated for about 4 minutes. John, it was poof. It was greasy kid stuff. It was powder. And so then people told me, said, well, Harry, just take the active site out, like Tom does and you do, and Marcetta does, and all my good friends do. Just take the active site out. It's a nice iron complex, looks pretty robust. But as you know, what we've learned in this field over 30 or 40 years of working, when you take the active site out of a protein, it doesn't work anymore. Because inside the folded protein, there are all these weak interactions, hydrogen bonds, hydrophobic interactions that tune the potentials and what we call the reorganization energy for electron flow. Things like that are crucial to transfer electrons at right potentials, they go away when you take it out. So I know you and Tom and Marcetta are spending a lot of time trying to rebuild these things so they come back into the sweet spots. And I urge you to continue this because this is a really important thing to do, okay? So keep your students working. Don't let them go home at night. They're up here. Tell them to work around the clock. This is urgent. All right. Well, then we started a worldwide effort. We started a worldwide effort to make molecules that all the synthetic inorganic, including my group, many other groups around the world, we started a worldwide effort to make molecules out of iron and cobalt that actually were very good hydrogen evolving catalysts. And we were very successful. We now have over 100 working catalysts containing cobalt or iron or nickel that are really very, very good hydrogen evolving catalysts, operate at low over potentials. Here's just a few from my group at CalTech. By the way, we worked out mechanisms for all of these experimentally, which I told some folks today. They were all wrong. Our first mechanisms are always wrong. So we get calls from theoreticians who tell us what's right. And I get very mad. I go home. Shirley wonders what's wrong with me. Gives me a big shot of Kentucky whiskey. I feel much better. I get up the next morning and decide the theoretician probably has a good point. I better do some more experiments. And every single time in this field, a theoretician has worked on this recently, they've been right. And we've redone the experiments and confirmed that they were right about it. And this has been a very important thing, Maria, for the field this interplay between theoreticians and experimentalists. For example, Mike Rose made this iron one that's heavily fluorinated. It's fluorinated all over the place. And I thought we'd park extra electrons in the ligands. They'd be redox active ligands. Sharon Hammes-Schiffer said, no, what you've done is stabilized iron 0. And it protonates to, and on and on. But these four here are really super good. I put this one up. Rosia Mercado was an undergrad in my group. She made this one, which Rosia, we thought this was going to be great. This one doesn't work at all. But Rosia was a wonderful gal, and I promised her I'd put this on my slide. She's a grad student at Berkeley now, doing very nice work. But now, let me show you the ones that really work. They're materials. They're robust materials. James McCone in my group made a nickel molybdenum alloy. You take nickel and molybdenum and you deposit them electrochemically, and you can vary the amount of molybdenum in the alloy. And we found, James found that 13% molybdenum is a sweet spot in a nickel molybdenum alloy. That works great. Then he found a way to make powders, nanopowders chemically, that you can drop cast onto silicon micro rods to make photo-cathodes, and they work great. Then at Penn State, Ray Shack's group, all these folks in some of our groups, Ray Shack's group made a real and enormous discovery that metal phosphides, simple compounds of metal and phosphorus, work just as well as platinum. They work in acid solution. The nickel molybdenum ones work in basic solution. We got the whole pH range covered with these three catalysts that are on this Hall of Fame. And of course, I have at least 50 slides of ones that didn't work. You have to realize that about professors. Most of the stuff we do doesn't work. And we cull out, we cherry pick a few things that work, so you have to remember that all along. Well, and Emily Warren and McCone and my group, and we coupled with Harry Atwater, who's in Nate Lewis, we actually turned these into these silicon micro rods covered with catalyst at the bottom, is nickel molybdenum powders. These things are very, very good. They're as good as platinum, and they contain nickel and molybdenum elements that we can scale up. So this is a big advance. Discovery of metal phosphide catalyst for hydrogen was a big thing between Ray Shack and Nate Lewis. My group has built these into working photo-cathodes. But these things, as you can see from the current voltage curves, you can get enormous currents at just slightly higher over potentials than platinum. For a photo-cathode, which can only absorb so much sunlight, you don't have to be as good as platinum. You're as good as platinum if you're close, because the catalyst has to keep up with the excitation by the sunlight. And so if you're close, you're just as good as platinum for this kind of application. And so this is what they look like. We have X-ray structures of them. You can make them in the lab here, Maria. You can make them in your inorganic lab. And you should do that. It's really cool. You don't have to do it. You can. By the way, how did those Bohr magnetons come out today? Did I get it close? How close was I? 382. You got 39? I get an A. I'm giving myself an A. That lab is cool, but you can do this in the lab. All you got to do is take a simple nickel salt or cobalt salt, be nickel acac, heat it up in an organophosphine solvent. It all comes apart, and the phosphorus and the nickel get together, and they crystallize in nanocrystals, beautiful, shiny black nanocrystals, which have this structure. Nickel is here, phosphorus is here. We think these work like platinum because we think we make, with one proton, we make a nickel hydride, and next to it, with the phosphorus is there with a lone pair that can park the proton. So we have a proton next to a hydride, and they can couple heterolytically to give hydrogen. We think that's how these work. I like the cobalt, there's the nickel one. I like the cobalt ones even better because they're much more stable. They work in half-molar sulfuric acid, and they give huge currents at low over potentials. And so we picked the cobalt phosphide one to make a real working photocathode to go with our other systems. This works in acid solution beautifully, just as well as a platinum system. And we coupled this, my group, Nate's group, a group in Denmark, Eve Chorkengorf's group in physics in Denmark, all of these folks. My student did all the work, and he got all these co-authors. Chris Roski did all the heavy lifting in this, and then he found out that we had a zillion co-authors, but he's first, so it's Roski et al., so that's okay. It's a completely working photocathode. So the bottom line is we still need you, Maria. We still need molecules, because there's a feeling, although we're likely in the big electrolyzers, we will probably use these materials. For some applications, we're going to need molecules to throw in the reactor every week. If they're cheap enough, this will be a good way to go at site. So you've got to keep going. And when you get a good one, please let me know. Okay, here's the big problem. We've got to turn seawater into oxygen. It can't be just regular water. We don't have enough pure water. It's got to be seawater. Think about it. 500 years from now, what do we got? Sunlight, seawater, nitrogen for the air, and carbon dioxide. And we not only have to make energy out of those four things, we've got to make everything else. All the stuff we're getting from oil, gas, and coal, we got to convert to a few things that we will never, ever run out of. And I repeat, sunlight, nitrogen, water, seawater, and carbon dioxide. That's it, folks. We'll have some sand. We'll probably never run out of silicon dioxide and sand, but you get the point. We've got to figure out how to do this oxygen evolution reaction from seawater, and that's a big deal. If we can do that, we can do everything else. So, tungsten oxide photoanodes, people think are probably good things. Have teamed up again with Nate to work on these, and a guy, Chi-Chi Mi, who's now at Shanghai Tech as a professor, a great guy. The valence band and conduction band are really nice. The valence band is deep, so if you make a hole in this, you're making a hole in an oxygen 2p orbital. It's pinned with oxygen 2p orbitals here, so this is stuck. And this has plenty of thermodynamic potential to oxidize water, but it's a multi-electron, multi-proton process, which is very forbidden. The one-electron processes of just oxidizing sulfate to SO4 radical is kinetically so much better that that's what happens. If you plunk tungsten oxide and sulfuric acid and irradiate it with sunlight, what you get is peroxy disulfate. You get a sulfate radical which couples, which you then have to go other steps to turn into oxide. So bottom line is we need the catalyst. We've got to put the catalyst on these things, and we have to lower the band gap. First, let's get the catalyst. Nocera gave us a catalyst from cobalt. He gave us a very nice catalyst that he made from electrolyzing cobalt solutions and anotically and getting this cobalt oxide kind of cluster material, which apparently is active if you make it up to cobalt-4. And Kyung-Chin Choi, who was at Purdue at the time, is now at Madison, Wisconsin, put this catalyst on tungsten oxide to make a fairly decent integrated photoanode catalyst, tungsten oxide and cobalt oxide, which does split water to oxygen, but with very, very low efficiency. And the problem is the band gap of tungsten oxide is too high. It's 2.5 electron volts. That means it's yellow, doesn't absorb a lot of sunlight. The challenge here was to lower the band gap to 1.9. And Shishimi, my guy, did that by a reaction that you don't want to run here. You can run some of the others, but please don't run this one. He jammed molecular nitrogen into the middle of tungsten oxide. It's not chemically bonded, it's just jammed in there. And what it does is it expands the tungsten oxide lattice slightly, so the conduction band, which is a bunch of 5D anti-bonding orbitals, drops like a stone. The valence band is oxygen P, it's pinned, but the anti-bonding level can come way down if you pull the tungsten slightly apart. We had a very hard time publishing this paper because no one believed we could put molecular nitrogen into a tungsten oxide lattice. And so this paper was rejected several times. When you do something really interesting, your paper will be rejected. I want you to remember that. Don't get depressed. If your paper is rejected, it's either really crappy or it's a great breakthrough. And so take the high road and be sure it's a great breakthrough. Think it's a great breakthrough. This was a pretty big breakthrough. We already had the Raman spectra of nitrogen in there. It's only 8 wave numbers shifted from free dinitrogen. N15 is right. So we knew what we had, but we sent it to Brookhaven so they could lay the hands on it up there, the fancy stuff at Berkeley. We sent it to Berkeley first and lay the hands, and then one referee sort of said, well, I don't believe anything at Berkeley. They're too liberal. and so we sent it to Brookhaven. At Brookhaven, this guy is at Brookhaven. Peter, however you pronounce his last name, I call him Peter for obvious reasons, but he said with some very fancy stuff, yes, Harry, you've got the nitrogen, just say where you said it was. And so we got the referees finally gave in and we got it published. What this does, of course, and the nitrogen's in there, it's very stable. You wouldn't believe it, but it's just free dinitrogen. You can heat this thing up to 600 degrees. You have to melt it before the nitrogen will come out. So this is a stable photoanode that works all the way out to red light to split water. This is a terrific thing. And if we could only figure out how to do this rationally, we'd be in good shape, but we haven't figured out how to do anything but this one-off one now. So now let me finish up. Got a few minutes left. We're looking for the world's best. I'm going a little too fast. We're looking for the world's best water oxidation catalyst. This is the one in green leaves that we've been living off. Once again, if you make this without the protein around it, it doesn't work very well. The manganese ones are horrible. But the nickel iron is the key. The nickel iron catalysts are by far the best. And Kyung-Chin Choi showed us that with nanoporous bismuth vanadate. She layered nickel and iron on. There's a big debate of whether iron is the catalyst or nickel is the catalyst. You'll see which side I'm on in a minute. But on the basis of this work of Kyung-Shen Choi's, we decided we would start making heterogeneous catalysts by a laser method that we've worked out that I'll finish up with. What we do is we train a triple YAG, a high-powered laser, on the metal target surrounded by water. When that 355 nanometer, 9 nanosecond pulse laser hits that metal target, it could be iron or nickel, it blows it up. Enormous energy blows it up to a temperature that we estimated is about 70,000 Kelvin. In a plasma, confined in the liquid, so it's under incredibly high pressures, and by the time we can measure the temperature by oxygen emission lines, the temperature is between 3 and 10,000 degrees Kelvin. So in this enormously hot plasma, confined in high pressure, Sean, a shock wave hits it and it spits out beautiful nanoparticles. It's a wonderful synthetic technique, whose sizes and compositions we have under complete control. The size depends on the laser pulse energy and the pulse length, and the composition depends on what we have in solution. If we want to make multi-mixed metal ones, we have an iron target, we put nickel nitrate in solution. We get a nickel iron catalyst. We've put more and more metals in solution. We get multi-metal nanoparticles. It's a miracle. There's the cobalt oxide one. Our cobalt oxide doesn't look anything like anybody else's cobalt oxide because we use low pulse energies, and it's quantum confined. It's quantum confined, so it's yellow. It's not black, it's yellow. It's a 2 nanometer quantum confined nanoparticle, and boy, is it a great catalyst. Because we don't get anything that's on anybody's phase diagram. These are all super rapid, condensed systems that aren't thermodynamic products. They have catalytic edges everywhere, and they're fantastic catalysts. So we decided to go to the nickel iron ones with an iron targets and nickel in solution. We decided to go all out and make iron nickel titanium, iron nickel titanium lanthanum. These are the 3 winners. In fact, in 1 molar sodium hydroxides, where you run the big electrolyzers, our catalysts are more robust and more active than any known catalyst. There's our 3. Iridium oxide was a previous winner, which is not scalable. Our nickel iron ones are very, very scalable, and we can make them in large amounts with this pulp technique, this laser synthetic method. The question then is, are there metal oxo intermediates? And this is what I've spent my whole life working on, metal oxos, which I'll talk about tomorrow. I'll explain all this tomorrow. But you can only make metal oxos on the left side of the periodic table. You can't make them on the right side. So if they're metal oxo intermediates, the active site has to be iron. Everybody in the world by this time said it was nickel. All the battery people, everybody said it was nickel. I said it was iron. And it is iron. I'm getting a lot of grief for this, but the reason it's iron is because of the oxo wall that I've developed over the years. I have shown that metal oxos don't go beyond the iron ruthenium osmium link, so nickel's on the wrong side of the wall. I'll explain this wall tomorrow. But the wall is there. You can't make an oxo beyond my wall. My wife has been giving a prize for anybody who could make one beyond the wall. It's a 50-year prize. It's worth a lot of money now. All you have to do is bring me a crystal of a metal oxo beyond my wall, and my wife will write a check, won't you? Yeah, she just verified. So we put these catalysts in acetonitrile. We put just enough water, polarize anotically so we can make the intermediate. It's a 6-dioxo iron 6 intermediate. The isotope substitution works perfectly. We've done Nussbauer on it. Most of it's iron 3, of course, but the catalyst is there in an iron 6 position, isomer shift for iron 6, cis-dioxo. And if you don't like that, ligand field theory predicts for only a D2 tetrahedral system, there'll be an atomic line which we call a spin flip, that's in the near infrared, which in ferrate is at 1613 nanometers. It's a very sharp atomic line. When we polarize azonotically, we're a little off of that, of course, because we've got this iron 6 embedded in this material. It's not ferrate, but it's close. It's sort of a kind of pseudo-ferrate. It's got this sharp atomic line. So there's no doubt about this being iron. And so if you go back and look at all the old nickel catalysts in the battery field, if you go back and look at all the nickel catalysts and electrolyzers, the alkaline electrolyzers, you find they all have a little bit of iron in them. And if you rigorously take the iron out, they don't work anymore. So it was always that little bit of impurity iron that made these catalysts. And so now the world is, we're about even now, the split between the nickel people and the iron people. My group is growing. Their group is going down. We're going to win this ball game. And then we published the mechanism with iron 6 just a few months ago in Joule, but our mechanism, as usual, is too obscure to figure out. So a guy named Holger Dow in Germany wrote a paper on our mechanism. He liked it a lot, but he explained it much better. So I put his explanation on this slide. Thank you, Holger. Holger's, by the way, a nickel guy. But he was very happy to write a paper on our iron catalyst, going through the dioxo, the side-bonded peroxo, oxygen off here, and relate it to the S states in photosystem 2. So now we've added, there are now 3 mechanisms for water splitting. These 2 have been debated for years. This one is the Yale mechanism for water splitting in photosystem 2. This is the Stockholm mechanism, the 2 mechanism. These 2 groups have been fighting for years about which one it is. My guess is not either one. I think it's my mechanism. Right here, where you make a cis-dioxo that goes to a side-bonded peroxo, then makes the OO bond on one metal and comes off as oxygen. And interestingly enough, the theoreticians have never, ever calculated this one. They've always been calculating either the Yale mechanism or the Stockholm mechanism. And the Stockholm guy says the Yale mechanism sucks, and the Yale calculator says the Stockholm one sucks. And I'm trying to get the theoreticians now to calculate this one, because I think this may be a better one. But there may be a multiple group of mechanisms. So this is the big deal. This is what you came to hear. This is the bottom line. If we can split seawater, we can do anything you want. Because with free electrons from photovoltaics, if we can split seawater, we can make hydrogen, as I showed you, for fuel. We can repurpose the anode to oxygenate methane to make methanol, the same anode. We can reduce CO2 to water at a cathode and then split the water to make oxygen for Mars missions. So NASA is very big in this, because this will allow people to live on Mars. There's a big thing here. And we can also make materials from CO2 from the electrons we get from water splitting. And this is the biggie. We can replace the Haber process with a solar process, where on one side we'll have a water splitter to make the hydrogen. The hydrogen, when the regular Haber process then can make ammonia without release of this enormous amount of CO2 that the Haber process does now, because the hydrogen from the Haber process to make ammonia comes from natural gas. Partial oxidation of natural gas, which generates an enormous amount of CO2 for the planet. And we can get rid of that if we can convert it to solar. We can do even better than the Haber process if somebody can figure out how to make a nitrogen-reducing cathode. We don't have that yet, but if we can make a cathode to make nitrogen to ammonia and an anode that splits the seawater, we'll have a full solar thing for fertilizer and food. This is what our catalyst looks like. It's incredibly active. Hydrogen, oxygen streaming off of this. There's our metals. That's what it looks like. It's a layered system. So this is what we're going to do. Let me get there. This is what we do. When we started this work, we thought this would be too expensive. The old-fashioned way of having a separate PV device and just a big electrolyzer with the anodes and cathode, an enormous electrolyzer which you can run several amps, make enormous amounts of material, a separate PV device. When we started this, that would have been much too expensive. Now, 10 years later, the PV is so good. The PV is so good, getting electrons cheaply, that we can afford to use the wires. That we lose efficiency in the wires, but we can afford to do that now. Plug it into an electrolyzer. And if you look at all the efficiencies now, we can build a 20 or 25% overall sunlight to fuel and to everything else thing. So this is looking really good now for just the next few years. We're gonna do it. And I got a lot of people to thank. Here are all the postdocs and students, undergrads. There are a lot of undergrads up here, grad students and postdocs who've worked in our program, CCI program, all over the world. They've worked in our program. Here's where they are now in academics. I rest my case that we have generated human capital that's going to make a huge difference as time goes on. You can read them all. Ones in boldface have contributed a lot to this talk. We've also got people all over industry and government. And these are all kids in Harvard, MIT, CalTech, Stanford, Illinois, Chicago, all the places in our program who've worked in our program over these years, and I thank them enormously. We have an advisory board that's not just a rubber stamp board. They've been giving us lots of advice over the years. They meet with us all the time. They're not just names. They're people who've interacted with us. I owe them an enormous debt of gratitude. We have an annual retreat. This is just one we had at Newport Beach. These are all of our PIs and postdocs and students. And this one at Newport Beach is to give you a feeling for the camaraderie of this group. And these are the three people who developed this pulp method, this new laser method of making materials that I think is a very, very important method, because there's all kinds of materials you can think about making this way. And you took time for the introduction. I've done my time. Sean, I want to thank Sean again. Kathleen, thank you for being in the photograph with me. and for putting up with me. I want to thank all the students that I've talked to and sharing your work with me. I thought it was just fantastic. I'm looking forward to tomorrow, to seeing you guys all again and following up. And thank you all for coming and for your attention.
So thank you, Dr. Gray, for a wonderful talk. I think we do have some time for some questions from the audience. If
yeah, we got a poster session.
We do
right after this, which I'm very much looking forward to. So, and then there's food. I hear there's food. That's why we have a crowd here. I've been around. I know why it's a crowd.
There are mics around the room. If somebody has a
question,
question, maybe some of the students first.
I get a student question first.
No pressure.
Come on. I want a woman student, Nancy. You're right. Has to be a woman student. Nancy has insisted. What's wrong? You weren't shy this morning? Okay, let's turn to the men.
There's a question over there.
Okay, where is it? Oh, here.
Aged.
You look like a student.
Very aged student. Actually, I'm a practicing artist.
Oh.
I'm a painter, and I work with watercolor primarily. As I avoided oil paint after I finished in art school, I avoided oil paint because you had to douse yourself in turpentine before you could go to the bathroom. So that wasn't much fun, and it really wreaked havoc with your nails. But I'm wondering two things. One, the presentation is, of course, over my head. I had no idea what I was looking at. Your leading us through it was absolutely fascinating, and I just wish I had
I
the.
decided not to dumb it down, actually. I decided that this audience was worth a serious talk in this field, and I decided deliberately not to dumb it down. It was the real stuff.
Apparently so.
Got tonight, so I'm glad to hear that I got through a little bit.
You did. So the question is, how are you making this safe for the students who are working with these potentially lethal materials? And secondly, in a very, very shallow, but one that's dear to my heart, is how to make it graphically more appealing. And if you want to promote this out into areas of different kinds of less stratified structure of research.
So make it interesting to you.
Yeah.
Well,
Get
stay
it
there.
down to my.
Stay there, and I'll tell you. First of all, we care deeply about safety in the chemistry community, and we have extensive safety training.
Good.
Before we let anyone touch anything in a laboratory. We sign off. We have extensive hands-on things. We have videos. We have situations and so forth. So we've had a lot of very serious accidents in the chemistry community. We've had deaths from fires and all sorts of things. So we're very, very anxious now to make sure that everything we work very safely in an environment. People don't work alone.
Good.
They work in groups. If it's at night, they make sure they work in pairs. They discuss, in our place at CalTech, we discuss the experiments extensively before we start an experiment and look at all the possible places it might go wrong and the things, particularly if we scale up a synthetic reaction that has some potential for danger. We go over it and over it to discuss it. So we take lots and lots of precautions and do lots of safety training. Now, chemistry is dangerous because we're working with very energetic chemicals, and if you're working with oxygen and reductants, in fact, you might wonder why you're standing there running cool when you're breathing in oxygen right now and your entire body is a giant reducing agent. You've got things in your body that will react with oxygen, and realistically, you should be in flames right now. Just to make the point that, we're human beings, we're living way off thermodynamic equilibrium. Our thermodynamic equilibrium is carbon dioxide and water and a few other things. So we're all living a kind of a life, a charmed life, but we worry about safety. Now the other part of it is when we replace platinum with these other elements, and make these so-called renewable fuels and green chemistry and things that are better, we have to be very careful that we're not going to pollute the planet with stuff. You can think of maybe a big electrolyzers that would make it be full of stuff that would be toxic and so forth. So that's another side of this. There's another talk in my area that addresses your concerns. And we're very concerned about it. There's lots of studies going on now that we don't want to solve this problem and create another problem. We don't want to solve the renewable fuel problem and generate a lot of materials which are going to pollute the planet even worse. So an enormous number of people are studying this now to make sure that the stuff we're making, the iron nickel catalyst, the tungsten oxide things and so forth. So these materials we're working on have been picked because they're also non-toxic. We could have picked things that if we scaled them up, we'd have a huge toxicity problem. But believe me, we're working on that, and we're concerned with it. Your concerns are our concerns. And I had, what was what other question? Oh, yes, the aesthetics. That's another area. This is going to be a huge job program for the aesthetics. There's going to be a whole new architecture and a whole new design for artists and for architects because of the incidence of the sun hitting things and the optimization of the sun hitting various photovoltaics, and there's all kinds of angles and so forth. And so the new houses, the new buildings are all going to have to be built with this in mind to optimize the collection of sunlight and minimize heat and so on. So there are going to be an enormous number of new opportunities in your area.
Just close with that when the artist was asked, well, why do you always wear black? He said, oh, or she, I will wear black until they invent a dark color.
Okay. Thank you for the question. You see, if you ask a question, I give another lecture. Others? Yes? Okay. Well, this is dangerous. We heated ammonium tungstate up to 600 degrees and melted it, and we flowed pure oxygen over the melt. And the pure oxygen flowing over the melt oxidized the ammonium cation to dinitrogen, literally right in the melt. And when we cooled the melt, the nitrogen was trapped. It's not a standard method. And our theoretician was the one who told us to do this nitrogen thing in order to drop the band gap. She had predicted that the band gap would drop by 0.5 volt. And what that means in real terms, tungsten oxide would go from yellow to red. We made tungsten oxide red. And she had predicted that. Then she told us if we could find a way to put in inert gases like neon and argon and particularly xenon, if we could put in xenon in there as an inert gas, we could turn tungsten oxide blue with a very low band gap, but we haven't been able to figure out how to do that. It would be a game changer, though, if we could figure out how to manipulate these semiconductors with inert materials inside. This would revolutionize all these areas, optical areas. But we haven't figured, the only thing we figured out is to flow oxygen, pure oxygen over molten tungsten, ammonium tungstate. And that's the way Chi-Chi Mead made it. So, it's a nice paper, but it may not be followed up with anything. Thank you for the question. What do you do, by the way? Well, that's good. I'm very friendly with retired organic chemists. Well, organic chemists have made an enormous change now for materials and all sorts of great things. So. And more, and even more. And now electronic materials. There's even a big revolution in organic solar cells. And there's all kinds of things. So I have forgiven all my organic chemists, and I've apologized to all of them for anything bad I ever said about them.
I think that's all the time we have for now, and I'm sure Harry would treat some questions
I know my
later
students
on.
will ask me stuff in private, so it's okay.
Before we end, I just want to say a couple of closing remarks. The grant that made tonight possible also includes funding for students to conduct research. A portion of the award will support 2 undergraduate students to work collaboratively with a faculty member on a research project in the summer of 2019. So
great.
if there are any PC chemistry or biochemistry majors in the audience who have been inspired by Professor Gray's talk, we will be accepting applications in the summer. for summer research opportunities in the next few months, so be on the lookout for how to do so early next semester. I'd like to thank the Dreyfus Foundation for funding tonight's event, as well as the faculty and staff who helped organize this event, in particular Kathy Baer and Shannon O'Neill for their help. And thank you again, Professor Gray, for a wonderful talk. We are truly honored to have you visit Providence College. We invite you all now to join us for a dessert reception in the Fiandela Great Room, where you may also enjoy some of our students' research posters. So thank you all again for coming, and safe travels home.